Okay, so let's continue. Um, so by the way, next lecture, please bring your computer. I'd like to try to install some computation assignment using Phoenix. Okay, so Phoenix is a code, so I will actually provide instruction on how to install it. How many of you have heard about it before? Okay, so that's good. If not, that's fine. Okay, I can. We can actually easily install it without any issues, and then I will explain how to using it to do some research. Some not research, to solve some basic problem. Okay, so but notice that in general, so Phoenix is a very powerful library that allow you to implement the code really quick, but you don't get the chance to assemble the details like gases integrations and all the other details. So it's not a so I guess in analog, not so accurate analog, if you're the user of the library, you can think about it like instant noodle. Everything is pre-packaged for you, and then you just add some water. But if you want to know what is the detail of the entire manufacture process, you probably need to use MATLAB or Python to implement everything from scratch. Okay, but here we kind of make the choice so that you can I'm assuming that you know how to assemble a matrix, okay, from a local form, and then I'll just skip that part and give you the tools so that you can quickly assemble a finite element model, okay? You see what I mean? But by doing that, you're giving up some flexibility and some details implementation experience. So it's a trade-off, okay? Do you think so? You use like, you know what I'm talking about. You can write a divergent operator, okay, gradient, whatever, but you don't necessarily need to manipulate it in detail. So it's a good or bad, okay? If you know what you're doing, that probably doesn't make a difference, okay? Okay, so now before the break, the most important equation that we find so far, which would be used throughout the course, is actually the balance of mass in a very elegant form, okay? Interestingly, the balance of mass have no mass term there, okay, as you can imagine. It also have no density term there, okay, which is also something I really found it amazing the first time I work out the derivations, okay? Because actually what happened is that this equation, strictly speaking, is a balance of volume, okay? So balance of volume is not a physical law. There is no such thing. Newton doesn't derive balance of volume. The balance of volume is actually a consequence of two things combined, which is the balance of mass and the incompressibility of the constituent. Okay, is it true? Is that just these two is enough? Okay, so you say no. What are the other items? We talked about that before. No mass exchange. Okay, so actually, anyway, so we do using that to derive the equations. So whether this is necessary ingredient remain to be seen. But so far we can say that these three ingredients give us the balance of volume, actually lead to that simplified form that allow us to take out the fluid. Okay. Okay, so far so good. Now, can you using this to solve any to run the simulations? Now, to run the simulations, what I actually need to do is to count the degree of freedom and the constraint, right? Okay, so what is a velocity? Velocity is a vector. So in the 3 dimension, how many components do you have? You have 3 components, right? Okay, so 3 components for the solid and another 3 components of the fluid. Okay, so how many equations do you need to actually solve a system of equation with 6 unknown. I need any equation. It could be one equation, but I won't get a unique solution, right? Okay. To get a unique solutions, I need 6 equations, right? Oh, how many equations do I have? Okay, I only have 1 equation, right? Okay, so where are the other 5 equations? Okay, so I just want to motivate us so that we can solve the simplest problem by making even more assumptions. And what I'm going to do next is that I'm going to relax the assumption one by one until eventually you will find out that you need 7 unknown, not 6, to solve the two-phase problem. Okay, now, one of the general problem about poromechanics is that there's a loss of degree of freedom. Okay, you at least here you're looking at 6, you can reducing it into 1, but if that is actually under the assumption that there's no temperature effect. Okay, if there's a temperature effect, I add 1 equations. If I actually have a chemical concentration, I add 1 more equations. If I have a phase field factor, I add another equation. So I actually need to solve a very complicated equations. We will talk about the numerical aspect of the difficulty here. But now, let's not thinking about it. Let's thinking about how to solve this equation in the simplest way. Okay, so what I actually want to introduce again is actually the Darcy's law. Okay, so how many of you have heard about Darcy's law? Okay, so let me explain. Okay, I'm actually trying to reduce the degree of freedom. I'm going to say that the velocity, the relative velocity, or the Darcy's velocity more accurately, sorry. The Darcy's velocity is a function of some kind of gradient of a potential. Okay? Does that make sense? We're solving it for a lot of boundary. For heat conduction problem, we make the assumptions the energy flux is actually some kind of the gradient related to the gradient of the temperature. For Ohm's law, we're saying that okay, we also have an electrical potential. The gradient gives us the electronic flux or whatever. So Darcy's law is one of those laws that lead to elliptic boundary partial differential equations. Okay, so now this would actually lead to, so these have 3 degrees of freedom, okay, velocity. If they are the function of h is a scalar, is a potential, then I have 1 degree of freedom. Okay, so I actually reduce 2 degrees of freedom. Okay, I make that assumptions. Now, in fact, that assumption is actually supported by the experiment from Harry Darcy's, that conducted the experiment. Power mechanics course, you probably already know H is actually called the fluid potential, or sometimes you call it head. Okay, and this is actually equal to 2 components: the elevation head and the head related to the hydraulic. Okay, this is actually simply the elevation head is simply the height relative to the reference point, and the hydraulic part is related to the pole pressure divided by the intrinsic density times the gravity of the, okay. Okay, now notice here, this is actually the intrinsic density, okay, not the partial density. Okay, so it doesn't change over time. If you assume water is incompressible, that simplifies lots of things. So far so good. Now I want to write it, the velocity, as some kind of functions of the gradient of this potential. Potential here, this is a scalar. Okay, just like temperature is a scalar. Okay, this is actually a scalar. Okay. Now, can every vector be written as a gradient of something? Okay, let me ask you a question. If I have a vector, okay, a vector field more accurately, a vector as a function of positions, Okay, can it be always be written as some kind of potential? Meaning that can I always find the corresponding potential that if I take the gradient, I will get back the vector field. Okay. Can I in general? In some case I can. In what case I cannot? Just imagine that. If I jump, I cannot, right? Okay, if I suddenly have a peak, okay, so it suddenly go up, something like this, or just a pulse, okay, that actually happen then the gradient is actually doesn't exist, it's a jump, okay, so it doesn't work. Okay, so go back to the main story. Now I actually have these equations. I have the divergence of V equals to the plus the divergence of the velocity, Darcy's velocity equal to 0. Now I actually want to use the Darcy's law, which is actually restricting this as a function of k times the gradient of these potentials. Now the first question is that what is this k? Okay, K is actually called the hydraulic conductivity, and sometimes it's called permeability, sometimes it's actually called, so in different literature you will find a different name, but in here we would actually simply refer to it as the permeability. Now notice that there's something interesting, there's a minus sign, okay? Why is there a minus sign here? Okay, it's related to the physics of the water flow, okay? Now, if you want to generate electricity, you will need an upstream water and a downstream water, okay? So, and then this is upstream, this is downstream. What is the direction of the water flowing? Okay, imagine that there's a YouTube, okay, not the video. Okay, there's a water level here, there's a water level here. Which way would the water flow? Is it this way or is it this way? Okay, it will go move down, right? Okay, so but which part would have a higher elevation head? Which one have more head? Okay, point 1 or point 2? Point 1 is higher, right? Okay, so I'm moving from the higher part to the lower part, but then notice from the higher part to the lower part. Do you see that? So that's why I need the negative one, because I'm decreasing the head in order to, so the direction of the decreasing of the head is actually the direction of the water is moving. Okay, does that make sense? Okay, so that hence that minus sign. Okay, so what I'm spent so many time to say that because I have seen that minus sign getting omitted. So in which case what you're equivalent to simulating is the opposite effect. Okay, so but sometimes the code actually work because you have another bug to put another minus sign. So two things cancel out and you don't know why. Okay, and that I would confess it happened quite common, and you have to explain the whole way. And why is that? Why is that? You have another minus sign. Sometimes you're missing that and you think you cancel out, because a lot of time people didn't realize that when you do the integration by part, you also add a minus sign on the volume term, and they also have a misunderstanding on the integration by part, so two minus sign become positive and they never recognizing that. Okay, that's the two negative thing. Okay, just to be aware, I'm not saying anyone doing that, but so what I'm saying is that sometimes the code getting a correct result doesn't necessarily mean that you understand doesn't necessarily mean that it works. You also have to go through whether the reasoning is also correct. Okay, anyway, so go back to this. I would actually have these equations. Now what I would have is that if I look at the divergence of the Darcy's velocity, what I would have is actually, I can write it in this more compact form, and I will have or I can write it in the Einstein notations, which is actually equal to each other. Now, what actually happened is that what if I substitute the Darcy's law velocity, the Darcy's velocity definitions there, assuming that there's a linear relationship between the gradient of the potentials and the dusty velocity. Okay, so this is linear relationships. Do you know why it's a linear relationship, by the way? Okay, because K is constant. But anyway, if you can write a vector, if you get, so this is a vector, this is a vector. If you can actually write a mapping in terms of a matrix, then these are linear transformations, okay? If you cannot write it as a matrix, it's not a linear transformations, okay? You understand what I'm saying? Okay. Going back to this, so what we have is the following. If I actually substitute this here, I would simply have the divergence of the V equals to the divergence of the K times gradient of H. Okay, does that make sense? Does that make sense? No, it doesn't make sense. I need to put the minus sign, but okay, pretty close, but okay. So what should I do to further make it a one unknown problem so that I can solve the problem? Okay, so our equation is the divergence of the solid velocity plus the divergence of the Darcy's velocity equal to 0, okay? Now what if the material is rigid, okay? What if the solid phase never deform? Okay, if it doesn't deform, the velocity is 0, right? Okay, so this is actually how in the undergrad we draw the flow net. Okay, what is flow net is solving is actually these equations, this equation in particular. Okay. Do you know what is a flow net? Do you know what is a flow net in your undergraduate course? Okay, so now what should we do? Okay, I'm actually trying to take away, I'm trying to simplify as much as possible. So so by simplifying it, I need to make it very special. I need to make more and more assumptions to make it even simpler. So what are the choices I have? Okay, one thing I could have is that I want to write K in a more easily to digest form. Okay, so what do I actually mean is that, yes?
I have a question.
Yes.
In this equation.
Yeah, so I should put, yeah.
That's what.
Oh, that's the question you have. Okay, sorry. I think I just keep talking and forget to write it. This is, let me say, this is actually the Darcy's velocity, not the solid one. Okay. So thank you for pointing out the typo. Yeah. Okay, so I want to further simplifying it, and one way I actually could do is the following. I can play around with K, and then I will assume that the material is isotropic. Let me use a different color. So isotropy. Okay, what is the meaning of isotropy? Isotropy meaning that for different directions you get the same property. Okay, so yeah, a material that doesn't respond with a different behavior in different directions. So for example, if I have a layer material, okay, is not isotropic. Okay, if I'm assuming that this is isotropy, what actually happened is that K is actually now equal to a scalar K. Let me write a vector times the identity matrix, our identity tensor, or I can actually simply write the K component is actually equals to Kij is actually equals to K connected data Ij. Okay, this is actually just the same way writing it in a different form. Now, if I do that, what happens is that K is actually isotropic. So if the material is isotropic and homogeneous, the K can be taken out. Okay? Do you know what I'm talking about? So in this case, the divergence of the velocity, Darcy's velocity, would be equals to the minor of the divergence of the K gradient of H. However, I can actually take out the term as this is a K tensor, and then I would simply take out K, and then I would simply have the divergence of gradient of H. Okay, now that comes into another question. What is the divergence and gradient of something?
No.
Yeah, that's a Laplacian. Very good. K Laplacian H. Okay, you see the triangle go into the opposite side. Okay, so the definitions of the Laplacian operator is actually the following. You apply the gradient first and then apply the divergence. Okay. Or we can simply write it as, this is actually seems like some kind of second derivative, or sometimes we actually also write it like this. Okay, so what happened is that the divergence of the Darcy's velocity is actually equal to minor k times the Laplacian of the potential. Okay. Now, so we almost have our boundary value problem set up. So let's look at the solid size, and then let me try to write it in a very general form. So let's see how we can simplify the equations. Now let's consider the solid part. Okay, remember that we have that divergence of velocity plus the divergence of the Darcy's velocity equal to 0. Now I'm taking care of this. Now I need to actually think about how do I rewrite this to actually simplify the equations to get the diffusion equations. Okay, so as we explained before, we have the divergence of the velocity equals to the rate of change of the volume of strain, which is actually equals to the diagonal term of the displacement gradient in the 1, 1, 2, 2, and 3, 3 directions. Okay, do you know what I'm writing? 1, 2, 3. Okay, so I can rewrite it in another way. So this is actually second derivative of u with actually respect to the x1 squared. Okay. So far so good?
So the dot is not time?
Oh, sorry. I think I made a mistake here. I shouldn't write the second derivative. You're absolutely right. This is first one. You're absolutely right. Sorry. Okay, now I actually need to introduce another concept, which is actually again borrowed from the undergraduate soil mechanics, which is actually called effective stress principle. Okay, so what is effective stress principle is saying that, okay, if I have the total stress, that total stress would be equal to the effective stress minus the times the identity tensor. Okay. Now, what happened to your undergraduate course is that it's almost the same, but then the minus sign becomes plus. Okay, do you notice that? Okay, so why is that? Now we have the minor.
I think it's because when you take pressure, it's
Yeah.
positive and
Yeah, actually, yeah, exactly. So here we're actually using we're first deriving that in a more mathematical sense, in the sense that the positive is actually in the tensile directions. And in soil mechanics, in the conventional soil mechanics, compassive is actually in the given the positive directions, okay, just for convenience. But here, we are actually trying to derive the boundary value problem, so it's actually more convenience to consider the tensile part, the thing that expand as a positive, just to consistent with the mathematics behavior. Otherwise, everything has to be swapped, and it's just too difficult. Okay, you see what I mean? Okay, if you want to introduce something that otherwise you have to rework everything, and then including the deformation gradient, and you would need a negative deformation gradient, which is kind of really carry. So let's not do that. Let's go back to this. Okay, now if you take the trace of it, take the diagonal term and sum it together, and then take the time derivative, I will simply have this. Okay, so the P is actually just a scalar, okay? So if you take the diagonal term of identity, you get 3. So and then 1/3 of it would be actually 1/3 of 3 is actually 1. So if I take the mean stress, I will simply get this. This is actually the mean pressure. It's actually equals to the mean pressure of the volume minus P dot. Okay. So V is actually the volume, which is actually what actually happened in the undergraduate soil mechanics. Doesn't really consider the rhetoric at the beginning. Now I want to introduce a constitutive law, okay, to relate it to the volume and the stress. And I would actually introduce something called elastic. Actually, more likely a linear elastic constitutive law. Okay, so anyway, does anyone know what is a constitutive law? It's actually can be derived from phenomenological observation that related kinematic to kinetic measurement. For example, displacement to force, strength to stress, or actually the flow related to the pressure gradient. Okay, etc. etc. So here I will actually introduce the elastic constitutive law, and that is a linear elastic constitutive law. To be more exact, I'm actually saying that the divergence of the velocity of the solid is actually related to 1 divided by KE related to the volume deformations of the effective stress. Okay? And that would be actually also equal to 1 divided by KE times sigma dot plus P dot. Now, what is KE? KE is some kind of modulus. Actually, it tells you that if I actually apply that confining pressure, imagine there's a balloon, okay, and then it's underwater. Okay, the balloon inside have some kind of gas that are more dense than the water. Just imagine that. And I will apply the pressure. Okay, so this is actually the effective stress that I apply to the boundary. Okay, dot n, actually more accurately. Sorry, maybe just this dot n. Okay, I apply this stress to the boundary, and what happens is that it will shrink a little bit, right? Okay, so if the material is isotropic, it would a spherical object will become a smaller spherical object without become an ellipsoid or any other shape. Okay, so it just gets smaller. Okay, so what is the KE is the measurement. I'm assuming a linear relationship between the size and the stress applied on the confinement. Assuming that is linear is the modulus that allowed that actually changing the kinematic to a measurement to the volumetric measurement. So okay, does that make sense? So given the volume change, I would use the modulus to give me the stress, okay? So, or vice versa. So 1 divided by KE is called the compliance modulus, and KE itself is called the bulk modulus, okay? You learn it from the undergraduate course. Okay, so they are more modulars. Okay, some of them cannot expressing it as a scalar, has to express it as a matrix, second order tensor or fourth order tensor. We will actually talk about that later. Now, so what happens if sigma is constant? Okay, if the stress is actually constant throughout the space, what would happen? What would happen is that I would have the divergence of the velocity equals to what? So this term would cancel out. So that one would actually from not equal to 0 to become 0. So what I will have is that the divergence of the velocity is simply would be equals to P dot divided by KE, which is actually the rho f g divided by KE times h minus z dot. Okay, assuming that the elevation head doesn't change, then what we have is the rho f g times KE times h dot. Okay, so why is the z doesn't change? It's actually the assumptions. Okay, so if you're actually modeling an orange that you're throwing into the sky, then z should change. Okay, if you model a material that are actually filmed in some locations, you can assuming that the z doesn't change that much for infinitesimal deformations. Okay. Now, why is the p related to the rho fg h dot? Why is that? Okay, this is also the constitutive of the water itself. Okay, I need to. Now, the important thing is the following. If I actually doing this, okay, if I actually combine the elastic response of the solid and then the hydraulic term, then this term will lead to this, and then the divergence of the Darcy's velocity is actually equals to the divergence of minor k delta h. Now, if I combine the two terms together, what I would have is this equation, rho f g divided by ke h dot plus divergence of minor k, the gradient of h equal to 0. Okay, so what happened right now? Okay, so ke is the bulk modulus, rho f is actually the intrinsic density, g is the gravity constant. Okay, we all know what it is, and then k is the permeability. Now, how many equations do I have here? I have one equation, right? Okay, how many unknown do I have? Previously, I have 6 unknown. Right now, I only have 1 unknown. And that unknown is simply h, the potential. Okay? Do you see that? H dot and gradient of h, gradient divergence of h. Then I actually need to deal with a specific equations that have first derivative in time and second derivative in space. Okay? Which is actually also very commonly happen in physical simulations. Okay, what is this equation called? There's a very famous name. It's actually called the Richards equations, which is actually very common in hydrology. Now, this term itself also have a very specific name. It's actually called the coefficients. Okay. So have you thought about it? Who is in, does anyone is in environmental engineering? You are in environmental engineering? Yes, of course, I remember. Okay, so why is it called storage? You are the expert of Rich's equation, I guess. Okay, why is it called storage? It's very important. Okay, so this term has no spatial derivative to it. Do you notice that? There's no spatial term, okay? So now what it means is that, let's say K is actually equal to 0. So what happened? Okay, if there's no permeability, the water is trapped, okay? So does that mean you cannot change the potentials? You can still change the potential, right? But in that case, how do you change the potential? Yeah, over time, it can still change the potential. Okay, so, but what triggered that? What triggered that change? This is very ambiguous, okay? But I want you to think very hard, okay? So imagine that this is a room, okay? No student can come in and come out, but somehow there's less student here. So what's going on? Okay. So the door is completely shut and locked, okay, undrink state. And somehow initially there's 10 students, and you observe it over time, there's only 7 students, or maybe there are 20 students. Okay, what happened locally? Okay, so change of the potential is actually due to this KE not being infinite. Okay, there's a buck modulus is changing. So you're looking at the same control mass or whatever is undrained, but then it doesn't tell you the skeleton cannot be compressed or extend. Okay, so that can allow you to, you understand what I mean? Like the orange, okay? Imagine like the orange. Without periodic scheme, it looks like the permeability approximately is 0. Okay, does that make sense? Okay, can you change the hydraulic potential of the orange? You can squeezing it, right? Okay, does that make sense? But then, can you actually have any flow in and out from the scheme? You cannot, right? Okay, that's what I'm trying to say, okay? Now, if you wait for long enough to observe that physical phenomena, so what will happen? Okay, so if things eventually doesn't change, if t go to infinite, what will happen? Now, if t go to infinite, eventually, for these equations, not everything is like that. There are things that keep changing forever. Okay, so if t go to infinite, if you wait long enough to get rid of the rate dependent effect, then you reach something called steady state. Okay, what is the special thing about the steady state is that h is no longer a function of space and time, is only a function of space. Okay, so h dot equal to 0 in order to fulfill that, right? Okay, you see what I mean? Now, so what happened? If h dot is 0, I get back to these equations. Now, if k is actually isotropic, okay, then these equations would become divergent of h equal to 0. The divergent of gradient of h equal to 0, which means that the Laplacian term of h equal to 0. Do you see why even the h is not here? Well, because k is isotropic and homogeneous, so I take out k, and this is actually what happened. So this, in your undergraduate, this is actually the solution of the flow net. Okay, so that's why flow net work for anything with different permeability. Now, one thing that are actually important is that the divergence applied to this. Okay, so if your k is actually not homogeneous in space, then these two are not equal to each other. This one and this one are not equal to each other. Okay, this is very important. Does that make sense? Okay, so if you work for oil company, you have these K that are actually really low. Okay, and then you have the K is very high, and then K is very low. Okay, sandwiched together. This is called a reservoir. So the middle layer is called a reservoir. The top and bottom are actually the barrier. Okay, for example. Okay, so now if you're here modeling the boundary problem, you're okay. But if you model this here, then you need to actually take account of the fact that there are minor K here and this gradient H there, and that will lead to two terms. Don't take out the K. Okay, do you know why? Just according to the product rules. Okay, I need to take out the O. So what would that be? Okay, if K is not isotropic, that means if K is actually not equal to some kind of this thing, then it's actually anisotropic. So what is the divergence? What is the proper way to write minor K delta gradient of H? Okay, so let me try to do it. I would actually write divergence of dot K gradient H. Okay. Or I can write the divergence of K gradient H. So what should I do? Now the divergence of K times the gradient of H is actually a scalar, okay? So this is a vector, okay? You see what I mean? And then the divergence of a vector is a scalar, okay? So what is this? So how do I actually get the scalar equations? So okay, so this is the first term. Okay, what is the second term I need to do? What is the second term? K Laplacian H, but K is the second order tensor. It's a matrix, right? So Laplacian H is scalar, so it won't work. Okay, so let me do that in another way. So this is actually, I want to using that to introduce the Einstein notations, which is actually have this advantage to help us figure out what is the second term. Okay, I will write Kij, okay, and then this is a dot product here, so I would actually write gradient, I would actually write H, comma J, comma actually mean the derivative, in this case a gradient, okay, so spoiler alert, for scalar you cannot take a divergence, you can only take gradient, okay, it's already a scalar, okay. You can take you can make it anyway, so. Okay, now I actually want to take another divergence, okay? What does that mean is that I would actually write I. Why is that? Because in order to actually communicate the concept, I degrade, I reduce the rank of the order of the tensor. I would use the same notation I, so that it would be called a dummy index, and then that would actually make a vector become a scalar, second order tensor become a vector, or etc, okay? Or now, so what should I do? I simply need to do something very simple. I need to write Kij, comma I, H, comma J. This is the first term, and then I write Kij, H, comma I, J, I. Does that make sense? Okay, so what is this term? This term is the first term, right? Okay, what is the second term? What is the second term? That would be just k dot gradient, so k double dot, k gradient of h. Okay, does that make sense? Okay, so a gradient of a scalar gives me a vector's gradient gives us a second order tensor, and then I have two double dot indicating that ij and ji are both dummy index, and I actually just double dot because k, I am assuming that is symmetric. Okay, so this is a little bit of mathematics here. Now I want to ask another questions on the permeability, and that is related to the property of the Darcy's law. Okay, so just go back to the previous equations. I have the Darcy's velocity that are actually equals to minus k gradient of h. Okay, so this is our assumptions. I'm sorry, there's a dot here. Okay, what should the k look like? Okay, k could be a scalar. Okay, in this k, I write a vector, k as a k. This, let me use the tensor. Okay, k times identity tensor. This is actually legit. Now, but in a general form, k is actually a second order tensor or matrix. Second order tensor is like a vector, but now instead of having one direction, I have two directions. Okay, I will have to give a more formal definition later. So what should be the property of k in order to be physical? Have you thought about that? Can k be any number? So k in general, I will write it in 3D as k11, k12, k13, k21, k22, k23, k31, k232, k33. Okay? So what would be the property of this in order for it to make sense? Just think about it, connecting the physical world with some mathematical property. Yeah, it will be symmetric. Okay, this is wonderful. Okay, why do you want it to be symmetric? Okay, this is very good intuitions. Okay, so the first, okay, but why would that be symmetric? So in order to answer that, you can think about what happens if it's not symmetric. Okay, does that make sense? Okay, what is a nice thing about a symmetric tensor? The symmetric tensor have one nice property that we want, and that is the eigenvalues would be not necessarily positive definite. If it's just symmetric, it's not necessarily positive definite. You can have a symmetric tensor that are not positive definite, but your eigenvalue will be a real number, okay? You see what I mean? It could be negative, it could be 0, but you won't get a complex number, okay? For non-symmetric matrix or tensor, you can get a complex value, you can get a complex eigenvalues, okay? So why is it bad? Why is it that it's not something you want right now, okay? Okay, if it's not symmetric, okay. By the way, if you solve a Ladder-Boltzmann's calculations or whatever, and you solve the inverse problem, you may get a non-symmetric tensor just because of some boundary effect, so it's possible. Okay, but, okay. So if the material is symmetric, so if K actually equal to K transpose, something very nice happen is that the eigenvalue is real, meaning that no matter how you change the coordinate, all permeability values are actually positive. Okay, so the permeability component actually have a positive meaning. Okay, meaning that you won't suddenly violating that the water coming from upstream. Water will always come from upstream to downstream, not the other way around. Another way, you bring it up positive definite. So why do you want positive definite? It's also the same thing, okay? We want it to be, by the way, strictly speaking, it should be positive semi-definite. Do you know why? What is the difference between positive definite and positive semi-definite? Is that positive semi-definite accepts 0 eigenvalues? So physically, a material that have no permeability can still be justified. It just simply doesn't allow water to flow. So you should admit 0 but not negative number. So K also, you would accept that, you will assume that it's positive semi-definite, which in most cases we can just approximate it as as a positive definite. Okay, it could be. Okay, so far so good. Okay, so then we have the governing equations, and so what I'm going to do next is to introduce some finite elements. So everyone ready? Okay. Okay, so the goal of introducing the finite element is to introduce something that we talk about the theory, but if you actually only have the theory and never able to solve anything, then you know what is necessary to be true, but you never use that truth to actually predict anything, okay? In order to predict anything at all, you either solving it analytically or more realistically for arbitrary geometry, you will use the finite element or finite volume to actually fulfill our duty as an engineer to make predictions, right? Okay, so predictions is usually very valuable, in particular accurate predictions. Okay, so remember these equations. Okay, so Ke is actually a bulk modulus. I will assume this is a constant. Rho F, I will assume that is incompressible, so it's also a constant. G, I would also assume is constant. So in order to not keep writing this term, I will simply say, I will write it as this. Okay, so SS is the coefficient of storage. Okay, you just add a new terminology there. No new notation, not terminology. Okay, and then I would actually have this term, one equation, one unknown. Okay, so this is actually, okay, so if you solve this problem, what happen? If this is the only true, I give it to you. I even give you the measurement of permeability and the coefficient of storage. So what will happen? Can you solve for equations? You can find the governing equations, okay? So given the geometry, but you won't find the unit solutions, right? Okay. So let's consider a 1D case. So what is this in 1D case? In 1D, this would be simply this have a time derivative of h plus the second derivative of h. And let's say it's isotropic, it will be something like this, right? Okay, so let's say I solve for the steady state equation, so I take out this term, I only have this term left. Okay, can I get the unit solutions? I cannot. I'm simply saying that the second derivative is equal to 0, okay? So it could be many different solutions. But if I tell you that h at x equals to 1 is actually equal to 0, and h at x equals to 1 is actually equal to 1, then what will happen? Okay, what would happen? What is the solutions of these equations? Think about it in a geometrical sense. How do I make a second derivative equal to 0? Yeah, I just need a straight line, okay? Or straight line, if you take a derivative, you give us 0, okay? So now I pin h equal to 0, and h at x equal to 0 equal to 0, h at x equals to 1 equal to 1, I simply need to draw a straight line here, okay? That will be the governing equations. You can try it. If we take second derivative, of course, it's equal to 0, so that's it. Okay, what is this thing called? This is actually called boundary conditions, and you have two kind of boundary conditions. One is the Dirichlet boundary conditions, or actually we call it essential boundary conditions, which explicitly tell you the actual solution at that particular boundary. Another one is called the von Neumann boundary conditions, which is actually does not directly tell you the solution, but it tell you what is this at x equal to 0, for example, at some point. Okay. So what you can imagine, if I want to draw a straight line, I can either give you 2 points and you draw a straight line. Does that make sense? Or I can give you 1 point and the slope. I would actually able to draw the same straight line. I don't necessarily need 2 points. Now, the important thing to understand is that you cannot simultaneously prescribe the von Neumann and the Dirichlet boundary condition at the same locations for the same kind of unknown. Okay, so they are actually mutually exclusive to each other. Yeah, with that understanding, with that recap, let's actually write down the FE formulations. Okay, imagine there's a domain. Okay, the reason we don't want to solve it in an analytical way is that the world is not a square or circle. It has many different shapes. Okay, I will call this domain omega. Okay, now then I would apply the boundary conditions in some locations, and then I will call this gamma s, which is actually give me the natural boundary conditions. Natural boundary conditions is the von Neumann boundary conditions that give me information about the first stability of the unknown. And then the other one would be the essential boundary conditions, or actually the Dirichlet boundary conditions, which you probably learned it from Father Element. Now, the whole domain is actually including the union of the omega, which is actually the volume, and the boundary. The whole domain. Let me write it. The closure of that domain, or the whole thing, is actually where we define the problem is the volume plus the boundary. The union of them add together. The complete boundary conditions is actually also the union of the natural and the essential boundary conditions. By the way, there is another boundary condition called Robin's boundary conditions. What is the Robin boundary condition? Is that the boundary have another governing equation in smaller dimensions. Okay, but here we won't consider that. Okay, one important property is that, and let me introduce something. You get a new set which has no element by actually looking at the overlap between the natural and essential boundary conditions. Does that make sense? What it means is that you cannot have portions of the boundary that simultaneously prescribed by the Dirichlet boundary conditions and the von Neumann boundary conditions. Okay, it doesn't make sense, or you cannot. If you try to do that, you find that there will be no solutions. Okay, you understand what I mean? So if you try to do that, what will happen, by the way? Yeah, so what will happen in practice if you want to solve such a thing? In real life, you have to deal with those things. Okay, sorry. In a boundary value problem, you don't want to do that. But if you actually try to do that, let's say someone give you the equations, at most, you can find the least square solutions, okay? But you should notice that the formulation of the boundary value problem is actually wrong in the first place. Okay, you should never try to solve it, okay? You see what I mean? So, okay, so how many of you are already taking a finite element course? How many of you know what is a strong form, weak form, collision form? Okay, I'll go very fast then. Okay, I still have the notes, so I feel a little bit bad for not going over the notes. But since you already know, so I will go over that really, really quick. Okay, what is a strong form? So file admin workflow have the following thing procedure. I will start with the strong form, and then I have the weak form, and then I will have the Galician form, Galician approximations more accurately, and then finally I would actually come into a matrix form. Now this is the workflow of the deviations. Okay, and then in the literature there are people playing around with all this workflow. Okay, formulate a new weak form, solving the problem, governing equation directly in the strong form without the weak form. Okay, collocations, or modifying the definitions of the approximations, or finding a projections to change. Okay, those are all research topic, but in a more standard way, we were actually going over this workflow. Okay, the strong form is a complete formulation where if you have analytical solutions, you should be able to find it without any additional assumptions. Many years ago, when I'm still young, that I actually studied the weak form and the Galician form by Professor Tom Uspo. And I find it very confusing in the sense that I just see all the H that I put it on the superscript, and then it's the difference between the weak form and the Galician form. I don't know what that H is. So I just, whenever I put that, I just put an H on everything. And it become, but what is the physical meaning between the weak form and the Galician form? What is the major difference? Huh? Yeah, very, very good. Okay. So what is the Galician form mean is that in the weak form, okay, so it's actually a statement. Okay, it's a statement that you may or may not able to solving it analytically, and basically it's saying that given this a specific storage that are actually positive. Okay, so do you know what does that thing mean? So omega map it into a real number, positive real number. Okay, so it means that S is actually a field that depends on the position vector. You can get different values. Okay, and then I will write the boundary condition value as R. R is actually related to the essential boundary condition values. So some values in the boundary condition value will map it into a real number. And then I would also have the S that are actually the prescribed value of the essential boundary condition, also map it into a real number, because the potential can be, and the flux can be positive or negative. And then I will try to find H, which is actually the whole domain with the closure, map it into a positive number such that the following constraints are fulfilled exactly in the corresponding domain. First is actually the governing solutions. Okay, so V is actually the Darcy velocity is actually the minor k gradient of H. So H is actually equal to the prescribed values on the essential boundary conditions, and N dot V is actually equal to S. V is the Darcy's velocity on the natural boundary conditions. N is actually the normal vector. Okay, so when you prescribe a boundary condition, this is also related to the normal vector, not the tangential vector. Okay, so NH equal to HO, which is actually equals to this at T versus T equal to 0. Okay, what is the last thing here? Okay, is the product space of the space and time. Okay, you see what I mean? Or you can write R plus if you actually want to be more exact. Okay, so this is called initial boundary value problem. Why is it called the initial boundary value problem is because of this initial conditions. So H is start with initial conditions. So it will be called I, B, V, P, initial boundary value problem. Okay, H equals to H, X times T. Okay, H is the functions of space and time. That's what they mean. Okay, you're trying to solve the functions that are space, a function of space and time. Okay, so far so good. We basically just we do everything in the strong form. Okay, nothing. The first time I remember that was many. I have get a little bit interesting in the weak form. Okay, what is the difference between strong form and weak form, except being weaker? Okay, why is it called weak form? Have you thought about that? Okay, just a thought experiment. If I say that R equals to 0 everywhere is actually a strong form. Okay, now if I don't know whether R is equal to 0. I was simply saying that R, the dot product of R for a lot of equations over integration is equal to 0. Okay, does that imply R equal to 0? It doesn't imply R equal to 0. Okay, what if I tell you that W can be any functions? Okay, what if I tell you that W include all the functions in the entire world? Okay, does that imply R actually equal to 0 everywhere? Okay, what does that imply? That's a very good observation. It's very close. Okay, do you understand that? Okay, so let's say R. Okay, do you understand what I'm saying?
So
What is the difference between that two statements?
between R equals 0 and
Between this statement, this absolutely is a strong statement, or actually let me write it in a more complete way. It's not necessarily equal to 0. It's actually like this. Okay, if I write something like this. Okay. So what is the difference between this? Now that a lot of, sorry, also I need to add the W there. Okay, what is the difference between these two statements? They are very close to each other in some sense, but one concept is reach. Okay, so that they look identical, but they're not so much identical. R equal to 0 everywhere is actually meaning that you fulfill everything in the strong possible way. It's fulfilled everywhere, but R is actually not equal to 0. But I'm saying that the tri-function times the R, the dot product is always equal to 0, equals to the boundary. If there is no change, this whole thing is equal to 0. So what is the difference between the two? So here I'm actually, okay, if I say A, let me come back to a very important concept. If I say B equal to 0, and B is actually a vector, it implies symbol B equal to 0, right? If I say that A dot B equal to 0, okay, and A is a lot of different functions, what does it imply? Yeah, so what would make A dot B equal to 0? They need to be orthogonal to each other, right? Okay, so there's a very important concept that I changed from the strong form to weak form. Here, the weak form, actually, I'm trying to say that my statement, actually my weak statement, actually corresponding to the getting orthogonal to the child space, that's all. Okay, you understand the conceptual difference? Now, if I tried it with many different space and then they're all orthogonal to each other, you say that, okay, somehow it's pretty close to actually this thing equal to 0. Does that make sense? Okay, do you understand what I'm saying? So it's actually the concept between absolutely being 0 and then have some kind of being orthogonal. Okay. So if you're being orthogonal to a lot of things, you can argue that it's pretty close to 0. You can converge into the strong solutions. I can say that, for example, if B equal to 1, 0, and I'm just make up something on that, and A equal to 0, 1, B is actually obviously not 0, okay, but the dot product equal to 0, okay? So you have to put it into some kind of statement that I provide some constraint projection that makes sense and then check whether it's equal to 0. So your choice of the child function is very important to actually making the with statement make sense. Okay, does that make sense? Okay, so here I would actually have the with form, and I would assuming a specific function L2, and L2 stand for square integrable functions. Okay, what does that mean? Is that I'm actually writing this. This could be any functions, providing that the following is true. Okay, I can integrate these functions without getting something blowing up. Okay. And then I will introduce another space that are actually H1. Okay, this H stands for the Hilbert space, which is actually all the set of the functions in the L2, providing even more constraint is that the derivative of it has to also be L2. Okay, so this is more restrict. Okay, do you know why it's more restrict? Actually, I make it more smooth, right? Do you understand that? Before that, I just require that the function itself doesn't have an infinite value, so anywhere or blow up. Okay. Now I require some smoothness. I cannot allow anything suddenly change. Okay. You understand what I mean? If it suddenly change, then the gradient is actually not smooth. Okay. Okay. So why do I need these two space? Because this is the space you usually use to construct your finite element solutions. Okay, notice that you usually only have first derivative being in L2, which means that it allows the piecewise linear equations. Okay, so I would actually introduce two space. The child space, actually, I will call it maybe T, and then I write H equal to belong to the Hilbert space. Equals to this. Okay, so far so good. Now I'm putting more constraint on that set. I'm only searching for the H that give me that H supposed to be Hilbert space within a Hilbert space, and H has to be equal to the prescribed essential boundary condition on the boundary. Okay. Okay, I still don't know what H is. It could be sine, cosine, or anything. Okay, but it cannot be something arbitrary now. It has to be an element in the Hilbert space, okay? And then I will have a weighting functions. Okay, what is that weighting function? Give it to you is that I will write W, and then I will do this H1, and then W equal to 0. Okay. So why is W equal to 0 on the boundary? Can it equal to 5, 10, 1,000, 1 million? Complex number. Why is it equal to 0? Or maybe you can think about that. What if it's not equal to 0? I think things get clearer if you say that some things must have certain property. Then the easiest way to think about it is what if it doesn't have that property? What will happen? Okay, what would that happen? Okay, let me write down the equations. I will become clear, right? Okay. To actually make it into with form, I simply require the interpolation functions to be smooth, okay, in the Hilbert space, and I want my weighting function to be smooth. I never tell you exactly what is the solutions, okay? It could be even sine and cosine, it could be anything. Okay, what does the Galickian form did? In the sense of Galickian, which is initially he solved use a triangular mesh. Very important is that, Okay, typically I have two space, the child space and then the waiting function space. Okay, that space usually are spanned by the same shake functions. Okay, however, in some case, you may not want to use the same shake functions. You may want to use a different shake functions. A numerical method called SUBG. For example, streamline upwind Galicki method are using different space. There are other things that are used for different space for different purpose. Now here, I won't do that right now. Okay, the consequence of using this more exotic strategy is that sometimes you can solve an instability problem. Sometimes you have numerical unstable behavior, like you replicate this jump and you see this. Okay, which we would cover. Okay, if you don't do anything special and solve the problem, you will get this. Okay, and then but in general, you would assuming that the child space and the waiting function is identical just for simplicity until you find that it doesn't work. Okay, unfortunately in poromechanics, a lot of time it doesn't work for whatever reasons, and I would actually also talk about the strategy to overcome that limitation. Remember, in the strong form, I have this really compact I have this I have the Galvani equations. Okay, now I want to convert into read form, and then the first thing I want to do is to introduce integration there so that it become a global form where I'm actually imply the putting the wave functions. Okay, so this format where I actually put a wave on the residual functions is actually called wave residual statement. Okay, so this is called the residual. Residual is something we want to make it zero. I put a wave there, that become a wave residual statement. Strictly speaking, the finite element equation can come from two formalisms. One is the wave residual statement, another one is the Euler-Lagrange equations. Okay, the Euler-Lagrange equation would be derived in a different way where you try to find the Lagrangian and then find the Euler-Lagrange equations. Okay, so here we will use the wave residual statement just to make it a little bit easier. To understand, you have something you know is Lagrangian, you add a wave there, it becomes wave residual, and you add the integrations. Okay, so let me work out the details, and the rest of them is simply, if we remember, it's a very mechanical process, and that mechanical process always include integration by part. Okay, and I will simply write out the derivations before my battery die out. Okay, so does anybody know what I'm doing here? What is the name for this statement conversions? What is the meaning of converging this statement into this statement? It's just integration by part, right? Okay, you see what I mean? It's the okay. So that's what I'm talking about. Notice that there's a minor term here. Okay, you see what I mean? Okay, so this is actually something I like here because I would have a first derivative here for my rating function. I also have a first derivative on my interpolation functions. Okay, instead of having second derivative on one and then none for the other. Okay, so if I actually work out the details, so what I would have is that so this term would be actually equals to which is actually equals to, okay, and S is actually the prescribed values of the natural boundary condition values. So NBC. Okay. Okay. So okay. So far so good. So essentially, remember that what we want to solve is that AX equals to B. Okay. Do we have AX equal to B right now? We don't have AX equal to B, okay, but we're pretty close, okay? In the special case where H equal to 0, do we have AX equal to B? I do have the AX equal to B is hidden somewhere. So this term eventually will give us AX, and this term will give us B, okay? You see what I mean? How do we go from there to there, from one part to the other part? Now, let's go back to the flow. Is the flow. Okay, I will simply put all the H into, I will replace W with WH. I will replace and then I would actually replace H with the H. Okay, H means discretized. Decision to made here that are actually, but they are actually not necessarily identical. Okay, you can look the same. But then the more important question is that why it could be discretized. Okay, so there's a very important thing usually used in the Galickian form is that I'm going to change the space that I use. So there are two kinds of space. Okay, one is the finite dimensional space, one is the infinite dimensional space. Okay, so sine and cosine you can write it forever. The mathematical expression can go infinite. Okay, or you can have a lot of space that have that can be expressed with infinite amount of term. Okay, so what is the finite dimensional space is the following. I should need a finite number of coefficients to express the functions. Okay, so this is where the finite element, the word finite coming from choosing the right space. Okay, now there's one thing that I very ad hoc in the Galickian space because I actually don't know the solutions, but I have to pick the space to solving it. Okay, you see what I mean? So let me give you assumptions. Let me give you, in the file element, you probably know, if your choose solution is like this, okay, and you have one element, and then the element have a shape function that looks like this, can you ever solve these equations? You can never solve that equation. By the way, you can solve a projection of that equations that minimize some error, but it will still be a very bad solution. Okay, so there are two things that are very ad hoc in this step, but you have to do it. One is to creating the mesh. Another one is you choosing the basis functions that actually form the finite element space. Okay, the Galickian space, the most of the important job is to pick a finite dimensional space. Okay, that space, that when I say that includes two different things, choosing the mesh and choosing the basis function for the mesh. Okay, so you can have this domain represented by maybe 4 triangle. Okay, that would be bad. Okay, that would be different than this. Now that would be 2 different mesh, but that mesh itself can also be interpreted by different shape functions. Okay. Okay, so actually make the decision of the mesh and the basis functions or the check functions. There are also another so what after you defining the finite dimensional space, the most important thing is that the mathematical equation. Okay, so you all know what is the matrix form. So let me quickly recap it. Is that okay? So I find out I have a domain. Now I'm actually meshing it with some finite element. Okay, and then now I have a number of nodes. Okay, the nodes actually carry a very important important role here. It also carry the coefficients of our function, the function that we want to express. For the governing equation we have, our degree of freedom per nodes is actually equal to 1. Okay, this could be important for your global assemble matrix, but here is just make it very simple. So y is equal to 1 because h is only unknown. Okay. Now, the number of equations is actually equal to the, of course, the number of constraints, which should be equal to the number of unknowns, which is actually should equals to the number of nodes. Is it true? In general, it's not true. You want to minus the nodes that are actually in the Dirichlet, in the essential boundary conditions. Okay. Okay, does that make sense? You already know. You already prescribe those values. It should not be the equation of unknown. Okay, so and then NR is actually equals to the nodes, number of nodes on tau R. Okay. So far so good. So what I'm actually saying is that I still write h as a function of space. Now let's okay. Let's consider steady state case. This would this function is actually not arbitrary. It would actually only equals to some kind of check functions that are still the function of the space times the nodal value h. Okay, does that make sense? So you solve for the system, but then remember that unlike the structural analysis, you get the nodal displacement like in your undergraduate course or solving a truss, you get a displacement at the nodes. You actually still have the entire solution as a field. You're just expressing it, leveraging the nodal solution as a coefficient to express that functions. Okay, I only have 5% of the of the battery. So let's see how I can do. So okay, so I would actually need to we expressing the weighting functions as a check functions times a c. And what is this c? Okay, this is the weighting functions. This is actually the thing I want to try whether the governing equation is orthogonal to the residual. Okay, it's like a test. Okay. So what is the value of c? What is the physical meaning of c? So what is c? So that's okay. Let me ask. What should we see? Maybe I ask a different question. What should we see? This is used for my weighting function, right? What am I rating? So I think the file element is very easy to understand the procedure, okay? You just need to be a machine to understand how to form the matrix. But there's an idea behind the procedure. So that idea requires you to understand C, what is C here. You can describe in one English adjective. C is arbitrary. Okay, does that make sense? C is arbitrary, is any real number. Okay, why is that? You subject it to a test. Okay, for the entire space, you want it to be orthogonal to that space. Okay, sorry. I think we are until 140. 1240. Okay. Okay, so I'm running out of time. Okay, sorry. I really like that course. I can teach it until 5:40. So, but I think that it would be too much of torture. So, okay. So I think that we are a little bit slow here, but let me finish the final element implementations next time. Okay. Sorry. Okay. So far so good. So I think I'm kind of getting a little bit